So let's get started today. I'm doing more work on the visibility jam, specifically working on a visualizer, an animated visualization for differential equations. We didn't get to any of that differential equation stuff yesterday. We didn't touch that at all. We were just doing, well, I have it up here. So if you see here, if you're interested in the kind of work I do, you can support me. You can become a supporter or a member or a premium member here. And one of the things you get if you're a member is you can see all of the code. You can see all the code that I keep private. Well, not all of it, but you can see a lot of it. Like the stuff that I would do on stream here is all here, so you don't have to wait for me to have it finished to release it. You can get the like cutting edge alpha stuff all the time. And I was just looking at what I did on the flow effect stuff yesterday so that I could remind myself what got done. So let's see here. That's just changing the build script and the run script. I gotta make sure I have those changed again because I might have changed them back. So we'll be looking at those here. Right, so I changed the way I draw the particles. Instead of having this directly implement the trail effect, it's just setting up parameters for my new trail draw function, and then we wrote this trail draw function, which ended up, we pre-computed this array of unit Q values, and that might be slightly heavier weights than what it needs to be. In theory, we might be able to compute these Q values in a loop on the fly and emit our triangles from that. But a little scratch memory isn't gonna use up all of our memory. It makes things a little simpler, so I'm not too worried about that right now. But yeah, so this was just implementing that. This is all implementing that logic for the drawing of the trail. And I think that's pretty much everything. I do have some new to-dos that I left myself. All right, so this is where I want to start, is looking at the API and the architecture for particle updates. That is a little bit clunky right now, and I want to understand how it's working and fix it. And then, let's see, what am I building right now? Am I building flow effect? Looks like I am. Okay. So I know this probably looks like garbage coming through video compression, but this is what it's supposed to look like, so that's good. But there's a lot of like all of this. None of this is showing as none of this is animating a differential equation visualizer for us. This is just a particle effect thing that I did for the announcement video for the membership stuff. So there's like, you know, just special programming in here. I want to strip out all that special stuff and just have a blank slate that I can play with that flow effect. So yeah, it looks like the build is ready to go and we can get into this. So right now, the reason I say there needs to be improvement on the architecture of the particle update is there's a sort of like state machine inside of each particle. Each particle is ready, moving, or stopping. And then I use these functions here to update the position and state of the particles over time. And what I kind of think is happening here is there's sort of two different concepts. There's building up these trails that were like the trail data that we're going to submit is one part of it. And ticking those trails over time, like every frame, the end of the trail ticks backwards and stuff like that. That's one piece of it. Or it ticks forward, like we shrink the tail over time, right? So this is one piece of it. The other piece of it, though, is there's this logic of like so I have a certain number of slots for particles, and I want to be able to use the current position while it's moving. I want to keep updating that position, but once it's stopping, like I'm kind of using these to allocate out when a trail slot is available for reuse, if that makes sense. The logic I kind of want to be able to do. Why don't we do like a usage code first approach today? So position start, position delta, position stop. These are the old API. So I kind of want to be able to see, like, if I were to drop all of that. Okay. Let's see here. So that initializes all the particles. We're not getting rid of that. But this here is the old way of doing the initial layout. And the new way would be something like, okay, we know a particle needs to start existing. So maybe I want like a particle system actually. And then I have like a spawn function on it. That might be the kind of approach I want. So instead of manually managing each particle's state, I will just say, here's the way we spawn a particle. But you notice I no longer have to actually do this in reference to a specific particle. So I wouldn't need the loop to look like the particle pointer here could go away. Now, let's see. Here, we're looping over all the particles that exist, and we're saying if a particular particle is moving, we want to figure out its delta position, which we put into this variable d. And if the particle is outside of the view range, it dies, and if it's moving slowly, it dies. So this is a logic that applies per particle, right? And I think the particle system itself will simply contain... The interesting part here is that whatever we do, the flow effect is getting built in right here. Right, whatever the mapping is from P, and I also am probably touching. And where do those get used? Okay, so those are all eliminated already. The hue is the only factor I'm using to wiggle all of them around separately. if I were to drop that, then I'm only using the hue for the actual hue. Now they're all going to flow perfectly in sync together. No more of the extra chaos that I did have. Which leads to funny things like these boundaries being super sharp instead of fuzzy. Okay. But that means that this here is a function that takes p to d, right? We're really just saying, given this value of p, oh, I guess it's also using s, the time. It's using s, the time from... Okay. The time from the start of the animation. So moving state, we calculate. All right. Once it goes into the stopping state, it just keeps running the stop, eventually running the stop function, puts it back in the ready state. At that point, it spawns a new one immediately, right? So what's kind of happening here is I've bound together the logic for the particle system spawning new things. Okay, so this right here would be where I would put in, if I were going to keep doing what I was saying, this sort of thing would happen, right? We'd go anim old API else spawn new position, right? Something like this. And that's fine, but like, what about the rest of these? There still needs to be... Blanking a little bit on what the exact API is that I'm going to want here. So let's just say all of this is old API. Oops. If we're doing new API, then what we're going to get is something like we tick the whole particle system once per frame. So this just tells it to update every particle's position. Where do the trails get saved? I'm not sure. What am I trying to do here? Let me take a step back and explain what exactly I'm picturing. So I feel like something's still going wrong in my search here. Right now I have an array of particles, and I initialize them, and then I have these little state machines running inside them, and I also have a trail inside each one. I think that it felt like there's a way to separate this out, so that the trails, so that there's one system that's the system of trails, and you can kind of just send points to a trail, and when you stop sending points to a trail, you it's gonna die, right? It's gonna die all on its own. So that would mean you would do stuff like let me just sort of sketch on this side for a minute. Trail, position, anim, trail system. Maybe we have like a trail ID and a V2 F32P, right? And then we would have anim trail tick and anim, right? And so the idea here is this is keeping a set of data structures for trails, and so we would want something like this. So whenever I ask for a new trail, I would just get one as a U32. I would then update the trail by sending points to it, and that would grow the trail up to some maximum length. And when I tick, it would decrease the tail end of the trail. And as I'm doing these ticks, right, if I ever stop sending points, the trails get smaller and smaller and smaller. Eventually, the trail would disappear, and then it would be available to be reallocated. You know, a new could get that. Or maybe the U32s here would always be unique, so after a trail is dead, it would never get recycled, but we'd have like a gen counter and a index counter or something inside these, right? 16 bits of each or something like that. Now, why do I feel like that's something I want? Is that something I actually need right now? I think maybe the easier thing to do, because the other thing I'm trying to achieve here is I'm trying to go back and forth between making progress on the jam visualizer thing and keeping the flow effect intact as I go. So maybe it's just time to fork, right? Make a copy of the flow effect, call it my Diffie visualizer, and move these to-dos over to there, and leave this just to sit here. I'll probably delete it sometime soon anyways. But that way I can just flip the order here and do this part first. And I think if I did this part first, it would free me up, because I'd have many fewer details fixed in place, and I could start to sketch inside the empty space in the code what the Diffie solver might, or flow stuff might look like, and then maybe finally I would have ways of doing this. Yeah. Let's try that. So let's go over here to jams. We'll make a little Diffie viz. Folder. Diffie viz.c will come from here. All right, there we go. If I run that, same things as it was before, but now we're looking at running it off of this, so we are going to start to just tear things up a bit. I think that's going to make it easier. One other thing that occurs to me looking at this is we could take out the MP4 rendering stuff. I don't think we're going to use that. All right, so taking out all of this, let's start actually with this. That's nice and easy. MP4 out, you can go away. You can go away. This can actually become a build unit with graphical living over here. Very nice. And then MP4 out. Right, so file render. You guys are all out. Nice. Okay. And while we're at it, that means we can do anim draw is usually set up to do this trick where we do the render. We resolve that down to the sRGB frame buffer. Then it wants to read the pixels. I'm going to say no, don't bother doing that. We're not doing this thing in this particular program. So no pixels. That's going to help with frame rate a good amount. Now there are still 2 blits here. Am I calling get input twice? Yeah, I am. Okay. Whoops. Well, that explains the mystery I had yesterday that I brushed past. Yeah, you go away. Okay. Or rather, I guess you go away. But that's really only true if we're doing, yeah. So when we have, yeah, these are just going to be different. Okay. Right, so anim draw is saying go to sRGB frame buffer. I'm going to say we don't need that anymore because we're just going straight. We're not doing the thing anymore where we read pixels out. So why bother skipping the window? Why bother resolving twice here? Let's just have it go straight to the frame buffer. And that's not quite right. Okay, let's take a couple steps back and just see, was this the thing that didn't work? So this part works. And oh, these are probably not targeting the window. Yeah, so this doesn't target the window when I do begin right here. Aolo 2, yeah, for sure. We're really not doing any favors to the video compression with my animation thing. Begin, OGL end. So, in order to make this work nicely, I mean, the easiest method might be to say pull this up like this. Get rid of these. And then 0 here. Okay, so that's close, except we're losing the sRGB resolve if I do it that way. Right, if I want the sRGB resolve, am I going to have to go twice? I mean, that's not the best way to do it, but that's the lazy way to get it done. Okay. Why don't we have an sRGB back buffer? That's going to be living over in my inner setup, OGL and knit. Let's check that out. Win32. Okay, good. So this will be the wiggle stuff. Right there. I'm not seeing any signs of... And just so we're clear, is this the final one? How do I know which one is the... Here's our context. Yeah, this will be the final one. Let's go and look. Wiggle, choose pixel format, ARB. Is there some way to tell you that I want sRGB? There we go. Huh. I'm not seeing any sign here that I can create an sRGB window, like pixel format, which is interesting. Not finding it for some reason. Not finding it anywhere. Okay. Okay. I'm a little confused. I thought that was an option. But I guess we'll just run the blit twice. Once to resolve multi-sample to sRGB, so linear to sRGB convert, and then also multi-sample down to multi-sample to single sample sRGB, and then go to the window, because apparently I can't do this straight onto the window because I can't figure out how to set the pixel format to sRGB so that this would do the sRGB convert. I don't know. I don't like the fact that this is one of those OpenGL things. I don't like the fact that I have to specify what this operation is by setting types on the objects between them. It's lame. Anyway, so let's move on. Oh, look at these. These haven't been caught yet. Yeah, I can explain what the conversion does. Someone's asking what the conversion does. So this first conversion here does two things. I have a multi-sample frame buffer. That means it's scattering like, I think it's like 16 points that I have it set to do right now. Yeah, I have 16 multi-samples per pixel. So that gives me better anti-aliasing on fine geometry for free. And, well, not for free, but automatic. It's like, it just happens without me having to do the work. I just turn it on, and OpenGL, the driver, the card, they do the anti-aliasing for me. Costs a little bit more than if you just do single sampling. But I have to resolve that down to single color per pixel to actually show you the image. So that's one thing that this does. The other thing it does is this is in a space called linear color space, but your screen is in a space called sRGB. And so if you want to do color math, like if you want to add and blend colors, interpolate via, like, if you know about hue saturation value, because I'm using those here, right? We've got like saturation values and stuff. These interpolations on the saturation and value here wants to be converted back to RGB, and that RGB is in linear color space. And so it all gets rendered out in linear color space, and then it gets sent back to sRGB so that it can go to the screen accurately, because the screen is going to go through sRGB. Now, if you don't know what sRGB means, I keep saying that and you don't know, there's actually a perfectly good chance here for me to show you why you might want to check out the MrForth.com website and see what kind of stuff I do at the lab. Over here in my videos, you'll see I have an sRGB anti-aliasing deep dive video. I spent like an hour and a half, right? This is a video that takes an hour and a half to explain in excruciating detail everything about the sRGB linear conversion problem, how it relates with anti-aliasing, how it's done in OpenGL in particular. I've got like example programs in there that do like, where is it? Like this. We've got this thing here. One sec, it'll come up. Yeah, it's there for a second. It's a real quick flash. I'm sure there's a spot later where I just freeze frame on it, but I'm trying to catch it. There we go. So I compare, like, on the left and right hand side here we have with and without sRGB. So this is if you don't do any of the sRGB stuff correctly, you get stuff like this. And you can see, like, if you look at the blending here, it looks different than the blending here, right? And we're looking at things like the anti-aliasing and the brightness on the various shapes and the color fringing on the shapes and the spacing of the brightness, see white, middle gray, black, white, middle gray, black, right? Stuff like that. So I tried to be very detailed in that video. You can find it on MrForth.com. Go over to the videos tab and look at the monitor calibration video. There's also, you can click on the code, and there's just a public repository with that example code. So you can go get everything you need to know about it right there. And if you want me to keep doing deep dive research projects like that in the future, you can keep me going by supporting me by becoming a member. Yeah, it's the thing is, and I totally understand that it's a long video. The thing is it's a topic that is extremely subtle and confusing. It's very easy to get turned around because there's stuff about the human eye and perception, stuff about what's built into the monitor, stuff about what's built into OpenGL, stuff about what you assume color is like when you're programming with it in like default space, like the default, like with that with sRGB naive stuff. And if you really want to know what's going on and you want to understand, there's no easy way. I can't give you the real explanation in less time. So whenever you're ready, it's there for you to get the whole thing. But if you aren't ready, then you just gotta assume that like you're not gonna get this right until you know it, and you might as well ignore it. Like, it's a subtle difference. You gotta trust that I've done it right mostly. But okay, where did we leave off? We have, so we teared out the MP4 rendering stuff, and I'm gonna go through and tear out a bunch of other stuff here. So PRT hue. Yeah, we were saying let's just start by getting rid of, I'm gonna get rid of everything here that wouldn't really fit as part of the anything that wouldn't fit as part of the differential equations viewer thing. I'm just going to take it all out now. Search. Dun. I wanted to see something different. Search for the particle hues. We're using it there, so we're filling them in there. We're allocating them here. Let's allocate these right here. Okay, so that gets rid of some things. But now what we're going to do is we're going to say, okay, there's more stuff to tear out. There's this whole bitmap. I'm going to take the bitmap out. So bitmap h divided by tmax. Let's just throw in, well, let's see, t bitmap space bitmap y screen x spacing. We don't need this. Yeah, we don't have a bitmap, so we can't do any of this. Can't do any of this. Can't do this. So instead, we're just going to calculate delta x using something that we can do fixed functionality here. Nearest distance. Don't need that. Sine. Don't need any of this. Okay, so delta x. What we're going to do is we're going to go, delta x is going to be 2 times p dot x divided by video width minus 1 or rather 1 minus all of that. And then we'll throw in like times 3, something like that. Goodbye to you. All right, so what's happening there is it's all too slow to show up. So let's do like times 9, see if we can get a little bit faster so it'll show up. So all this flickering here that you're seeing, I don't know if you can tell what it looks like over video compression actually, but like there's little lights showing up here. These are places where the particles are spawning, where they are too slow as soon as they are born, and so they are immediately dying. And you can see that they start dying somewhere around this range, depending on like the y velocities that they have as well. So if they're coming in straight, they die right away. If they have some y velocity, it makes them a little faster, so they survive longer. We could, you know, just tune up the parameter that allows them, like, how slow they're allowed to go. But what we can't do is we can't guarantee that this will never happen, right? The robust solution here would be to do something like, hey, if a particle spawns in a location where the velocity is going to be too close to the death velocity, then just don't spawn it there. Roll again. Keep rolling random numbers until it's not spawning too close to the threshold, right? So if we're going to say particles die when their velocity goes under 2, then maybe a particle just doesn't spawn at a velocity less than 2.5 or something like that, if that makes sense. But you can see now we have all these particles that are kind of showing us the flow lines across the whole screen. So the next thing I want to do is I want to well, let's keep cleaning out anything from the flow effect video first. But if at some point I want to get to the point where we have simplified this down to a very simple, like P goes in and the D comes out, and start being able to like formally parameterize a differential equation and get out the correct flow effect. I also want to keep the flow effect inside of a range that's not the whole screen. I want it like in a square or in a box or a triangle. Like I want finite domains here, not full screen coverage. Okay, so let's see. Are there more things here that aren't actually relevant? T-clamped. Okay, so flow effect. I'm going to close the flow effect files since they are so similar. They're kind of confusing. T-clamped isn't getting used. Let's go like this, and one at a time we'll remove the things. Okay. So as things are getting simpler here, I think we're getting to the point where what we're going to end with is... Yeah, let's just go ahead and get rid of all that. And just say we're going to end with delta x delta y. Delta y is going to be... We could do something very similar to what we did here, but with h and y. All right. So now the reason we are getting this oval shape here in the middle is because we have a radius of how there are a couple things to change now. So now we're actually kind of stripping out all the fancy stuff that I did to make it into like a visual effect for the video. Now what we're getting left with is the actual way a differential equation flow field animation is going to look, which is everything's kind of flowing in uniform ways everywhere, and it's not changing over time. The flow field is fixed. Now we could play with animating the flow field too. That could be fun and a useful tool for visualizing. So we're already doing animation. We might as well also have the ability to take a parameter and change it over time to see that one parameter reshaping the field. But the fact that we're getting this oval here is because, one, everything's, we have these two different axes operating independently. We have a radius of 2 in the sense that when the speed drops below 2, we kill the particle. And so this is sort of the space where everything in here has a velocity less than 2, right? So, what we might want to do is we might want to go, let's pull out, we calculate D from P. Okay, some things I want to achieve. Here. So the special animation control stuff is getting pretty low. Let me just double check there's nothing else floating around from that. So here we're still loading in the bitmap. We can pull that out. That shouldn't break anything. Okay. All of this is totally normal and fine. Anim init, what are you doing? This is where we set up all the particles and stuff. So we're gonna call this diffeqviz init and diffeqviz draw now. Okay. There we go. Now we're starting to make this its own thing. I think we've stripped everything out there. So here are some things we got to do to start making progress here. Let's set up the visualizer constructs. So we want sort of an abstraction from the diff EQ coordinates to screen coordinates. So right now what's happening is my particles, right, they have a position on the screen, and that position on the screen is used, it goes into a function, out pops a delta, and that delta updates the position literally on the screen. So I've tied together where something is on the screen with its computation. But if I'm going to make a visualizer, I'd kind of like to be able to put it in like a box and move the box around and not affect the abstract space where the flow is calculated, where the differential equation will be turned into a flow field. All of that should be in an abstract space, and then that should be mapped onto the screen after the fact. You know what I'm saying? So let's think a little bit about how I can achieve that. Right now, the particles, this is where we start running into things where the way the particles work is a little bit funny. The particles do several things. They keep track of their current p-value, they keep track of the trail, and they keep track of a state. I think there's some other things I want to change too. So you notice how when we start, we kind of populate the whole screen with this rectangle, and so there's this like giant glow that spawns and falls in, and then as they fall in, they start spawning in random spots, and it becomes this more like uniform flow. I think there's kind of like a couple of waves of the brightness falling in, and it just sort of evens out very quick and becomes uniform after like 1 or 2 cycles, right? I'd kind of like to avoid having that startup goofiness, and the way I have to do that is I have to start thinking about spawning particles in using a spawning rule that is not use all of the particles up front, because I allocate, you know, like a few thousand particles, and then I just put all of them in at the beginning, right? They're just all put there kind of on a grid, and then as they fall into the hole, they start spawning in random spots, and they spread out and become more uniform, right? So the question is, if I'm not going to spawn them across the whole space to form a grid, how am I going to spawn them in? And I think that that deserves one of these guys. Ongoing particle spawn instead of spawn all at once, right? So, for instance, if during the init phase here, I did not do any layout work, what would happen? That's just kind of where I want to start here. What would happen if I just didn't do this, spawning them into a grid? So there they all randomly got spawned. So they're no longer in a grid, but they still fill the whole screen because they immediately are all ready to be spawned, and when they are ready, they always spawn. So I think what we want instead, let me take that out. We have down here this rule that if they are ready, we spawn them right away. I think we want to switch to a situation where we have some maximum number of particles available, and we spawn a few at a time, right? And so we could spawn them over the course of multiple frames right from the start. We can't do that right now because we decide whether or not to spawn them based on their current state. We keep them constantly going. We keep every particle on the screen all the time. So let's see here. Right, there's the stop rules. That tells us okay. So I think what we could do to get started, let's not spawn things when they're ready. This here will be flow of moving and stopping particles. And this up here will be spawning of particles. Right. The idea will be we'll want to figure out how many particles we're going to spawn each frame. Let's just start with a number. N equals 10. Might be really low. 40. Whatever. I'm going to loop all my particles. Yeah, actually, I'm going to do it like this. I'm going to loop all my particles. And for each particle, if the particle's state is ready, then I'm going to do the spawn logic. And I'm going to decrement n by 1. So now it looks like that right from the beginning. It starts off dark and fills the space. And that's if I do 40. What happens if I do 10? All right, we can start to play with this. So it takes a little bit of time to fill it up. But instead of the startup effect being we need we have this big like flash of bright and then it all has to fall in and even out. Now the startup effect, or now the startup cost is like getting to an equilibrium point by spawning them in as fast as they are, getting to the point where they're spawning in as fast as they're disappearing, right? And interestingly, I don't know of any easy way to ensure that there's no startup like moment, right? It seems like that's always going to be happening. But I am curious, like, as we play with the number of spawns, what kinds of different looks we get. Like, this looks like it's just using less particles overall. Than it was earlier. I also notice, I wonder, let's play with some other things here. Because I keep, you know, noticing that the video probably doesn't look very good across Twitch. And it's probably because things have to move pretty fast like this. So what if we did something like D equals V2 F32 scalar mul 1 over video FPS. Oh, right. Okay, so the D will still go like that. That'll still go like that. When we go to update, we're going to take D times the inverted frames per second as the actual change in position. So this will now be considered not just some per frame delta. This is the per second delta. This is the change in coordinate per second that we want to see. So now it's going to look real slow. They're moving 3 pixels per second. They don't even look like they have trails. It looks like points popping in. And so you can't tell if there's any flow happening there. But let's keep going because we're not quite done with this thought process. This is the P of a particle, right? So let's get to the point where we're doing that abstraction of the coordinate space a little better. The particle itself is moving around inside of an abstract space. I'm going to say, for now, let's just hard code our abstract space, and we'll get to the point where we can soft code it later. So we're going to say that the range of the abstract space is a unit square, like this. Less than this. P.y is less than this. Is greater than this. Is greater than this. Now that looks like that. We no longer care about the video width. We're going to use the abstract space width and the abstract space height. Max minus min. Height comes from the y coordinate. Yeah, you can go away. And then this is the min x value plus a roll against the width, and this is the min y value plus a roll against the height. So that's how we spawn them in. Grab the p value, do this. Now it's just going to be it up in the time in the may. All right, so now it's all crunched up into that point right there. Yeah, if I take my space and map it across the whole window, then yes, it's going to stretch in the x-axis. But I don't have to map it across the whole window. I can map it into a, a box of 500 by 500 in the center of the window or something. Right. Okay, so now I have them in their new unit box space with their unit box velocity limit, which is actually going to be, that's such a huge radius now that they're spawning in this much space. They're also moving so fast for the space that they exist in now. But we can't see any of it because we do all this work, and then when we go to draw it, it's treating those as if they're in the real location. So what we were going to do is we're going to create a rectangle that represents where we actually want this to happen. So yeah, I said 500 by 500. Let's do that. Let's do v2 f32 video center video mid equals v2 f32 video width video height video mid dot x minus v2 f32 rect dim equals v2 f32 500 500 rect dim dot x times 0.5 half rect dim 250 by 250 half minus half rect dim video mid dot y minus half rect dim dot y minus becomes plus. There's the rectangle. And when we go to draw our particle, in addition to sending down the particle that we want to draw and its hue, we're going to just say, like, what's the rectangle that it should get mapped into? Does that work? Well, that works if we assume the particle's always in that unit range that we hard-coded. Maybe what we actually want to send down is a transform, right? We want to send down a linear transform. So let me think. We need to say, yeah, we'll just throw this into the, oh, this is separate. Okay, let's do it like this. Anim box transform. So what we have right now is pretty easy. The X off is going to be video width minus 500 times 0.5. The Y off is video height minus 500 times 0.5. The X scale is 500. The Y scale is 500. So that's only easy because I chose the unit box. If I have to, later I'm going to have to say, given a, given two rects, I'm going to need a function that's like this. Given a rect and another rect, give me the box transform, right? And that'll be like, we have a source rect and a destination rect. We want to take everything in this rectangle, map it onto everything in this rectangle. And here's the box transform that achieves that, will be the function we want. So mark that there for working on later. Xform, perch draw. Anim box transform. And I'll just pass that along to the trail draw. And then what happens is whenever I go through here, after I get a p-value by reading it off of the trail, I'm assuming that these are in source now. So T0 and T1 are in source. So after getting a p-value, that way I have to do p.x plus equals x form x off p.x times equals x form x scale p.y y off y scale trail t NP, NP, NP. Trail T. Trail T. Okay, got nothing now. Not even up there. Let's see what let's see what Remedy has to say about this. Diffie-QViz exe. Xform equals right. Right. Let's just do a little helper here. That can be like, I don't know, it'll be out of organization here, but box transform v2f32p in out, anim box transform. Okay, too easy to get that wrong, apparently. Px times equals x form scale, px plus equals x form x off, y scale y off, y. P x form NP P x form. There we go. All right, so now it is a bunch of particles mapped into the space 0 that live in the space of a unit box that are being rendered right here on the screen, blown up to a 500 by 500 block. They're moving really fast, like I said they would. So let's go look at how we're calculating that delta. Our current equation here says that the change in x is equal to 1 minus 2 times the change in x normalized by the width of the whole space. So it becomes 1 or negative 1 on the edges. If we slow it down to say like it's moving at the far edge, let's have it moving at like 1/20th of a pixel at a time. Now it's too slow, but of course we know that our velocity here is pretty aggressive. So instead of 1/8, what if it's 1/500? Okay. So here are some things, some thoughts I'm having. One, you kind of lose the ability to feel the flow if things are moving slowly and they bunch up like this, but the bulbs are still super bright on the tail. So I think what we might want to do is we might want to start having the particles actually set their brightness based on, like, we might want to have them actually have smaller max radius is to begin with, for one thing. Yeah, I was adding and then multiplying, and then I switched it. That was a part of the. I was fixing a bug, so I didn't explain this, but I did I did it first with add then multiply, and then nothing showed up on screen. I thought it through and realized add then multiply was a bug. I meant to multiply then add, and I also decided to pull it out into a separate function, so that I wouldn't be able to make that mistake again in the future. My mistake for not explaining what I was doing there. I was fixing a bug and refactoring at the same time. But doing two things at once without explaining either of the things I'm doing will probably be a little confusing. Okay, so trying to make it a little bit more readable when the particles get slow. What's interesting is, like, I think that whether or not it's readable has a lot more to do with screen space stuff than the equation. So I think I might have to evaluate the velocity question in a slightly different way. I also think I might want to have random particles, like, because right now the velocity limit means that there's this, like, little bubble in the center where it's too slow. I think I might want to have each particle have a sort of random variance of how slow it's allowed to get. So some particles will, the density of particles will fall off towards the center at an uneven rate, so we don't get a cluster like this. You know what I'm saying? Like, I think that or maybe what we could do is we could say we'll kill particles not based on how slow they're moving, but based on how dense the space around them is. You know? If we set some kind of max density and then we scan each particle's surrounding area, and the more dense it is, the more likely it is to get killed, then we might be able to see the flow effect here, and we wouldn't need a velocity cutoff at all. Or the velocity cutoff could be very, very small, like very close to zero, like an epsilon value. Let's explore this. So we want, where's my to-dos? Okay. So we've done the abstraction in the sense that we have that transform now. Thinking about implementing this. Implement this. Screen space density particle death rule. Another thing we could do for fun is we could negate these, so things will flow out instead of in. You can see our flow field like this. Now, what's weird and funky about this is we're now looking at a flow field that sort of... All right, well, thanks for coming and hanging out, and thanks for the... and hope you have a good day. So this when the slope on the boundary points outside of the finite space, it kind of suggests that our finite domain is inappropriately chosen. Like, it feels like it wants to flow beyond and outside of the domain, but it still looks cool. It's still cool to be able to check this out. So this is what it looks like when things flow away from the center faster and faster as they get farther away. We could also flip it around, right? We could have them flow out at their fastest when they are near the center. So the way this will work is we have a number here that's between 1 and -1, and it points away from the center. We want it to be the case that when the sign remains the same, but that the effect tapers off the larger it gets. So what immediately comes to mind is to do something like 1 point f over the distance, right? Except this will have a singularity. So what we could do is do 1 point f over the absolute value of the distance times the sine of the distance. Right, so it'd go like this. Delta x equals delta x f32 diff x, something like this maybe. I don't know what that is. Not what I was expecting. Diff y, p dot y, y, delta x, delta y, diff y, p dot y, h, space, x, y. So they're symmetrical, but why? When this is a 0, we get a -1. And when this is a 1, we get a +1. You know, like this. So it points away with the sine of f32. Double check that does what I think it does. Slow it down so I can get a better look. Yeah, what is that? What is that? So things in this region are getting pulled into 0, 0 instead of flowing out, which is what I would expect. Something funky. When x is 0 and y is 0, Then this and this are both 0. The whole thing is -1, -1. This comes out as a -1. Oh, I don't have parentheses. I don't have parentheses. Okay. There we go. And then that's a bit slow. Maybe we can go with a little faster. Cool. Cool. All right, so anyways, this was just for fun. Let's back this up to delta x equals this, delta y equals this, flip the signs, set the speeds, and then we want to avoid this density, this on-screen density from getting so high so that we can actually see the flow effect still. And so yeah, let's see how we would do that. In order for that to work, we would need to know the transform that we're going to apply already right here, right? Because this is where we calculate if we're going to kill the particle or not. And yeah, so let's set the ab space min velocity. Let's set that down to be like machine epsilon f32. Right, real small. So the only way these things will die is if they get like right up into the center. I'm going to let it run for a minute because we'll be able to tell if it's killing them at all based on velocity. If this runs for a while and it stops spawning new particles. I could also find out faster if I increase the spawn rate by a lot. So yeah, I expect this will run out. But if it starts to spawn more, then we know that it does in fact kill the particles eventually. They're still going. That might be too small. Asking for it to get that close to 0. Yeah, I think that's too small. Okay, so not machine epsilon. This is probably too small still because I feel like right about here it should start spawning new ones. There's definitely just not enough motion in the center to justify keeping them all. So the cutoff can be higher than that. There we go. And see the bubble that it's creating now right there in the middle. See if it's smaller, if that still works. And this is based on the abstract coordinates, not based on the screen space coordinates. I think the density thing will be much more important for solving the screen space problem. This is more like a fallback. I just want to find a spot that's yeah, there we go. That's numerically large enough that it'll actually catch things very close to 0, but so small that it's negligible compared to the density, which is definitely the point that this is at. So I think this is where I want it to be. Nice. Next up, I want to do the screen space density thing, I think. So where do we actually compute the transform? That's question number 1. Put it right here, right before we draw particles. I'm going to have this graduate up a level and live here. So this tells us how we're going to map our particle systems space to the box on the screen. So what we're going to do is we're going to scan all the particles, and we're going to have to measure the density of the particle around each particle. So this could be costly because it could be a there's going to have to be a double loop if I do it the simple way, right? So like, here we go. If part J is moving, so we've got 2 moving particles. We're going to look at the diff between them. So V2 F32 sub part IP minus part JP. We're going to look at the squared length, which is this. Don't have a dot, do I? Diff.x times diff.x plus diff.y times diff.y. And if the squared length is less than, so we're interested in, we also have to do V2F32 pi x form anim box transform pi x form. We can do this one up here. So we get the transform pi, and we're going to do j. I think it'd be easier to just do PRT I PRTJ diff and then transform the diff, right? That should be the same thing, because we're getting a distance vector in the we're getting a vector in the original space and then applying the box transform to it. We don't want to try to apply the whole box transform, do we? We want to apply just the scale part. X form, X scale, Y scale. Right, we don't care about the absolute position of something like a distance back vector, but we want to scale up the X and Y according to the box transform. Yeah, that makes sense. And then take the squared length. If the squared length, now the density level, we're going to measure the density level by scanning, what is the radius of those? So I have a radius of 1. If something else, yeah, so we'll use a radius of 2, which means if it's less than or equal to 4, then it's touching me. And so we're going to have a little counter here that goes up. And so for each particle in my space, I see that go up. And then what's going to happen is if the counter is greater than 1, then we can do if prng, let's see, prng.h flip, do I have coin? Do I have pcoin? Yeah. prng roll pcoin, vars prng, and I want the floating point value here to be counter minus 1 divided by like 5 or 6, right? And so if that happens, then I'm going to mark it as stopping right there. All right, so that slowed things down tremendously because we're doing that n squared search across all the particles that exist. So we're going to have to think about a smarter way to do this next. Nice, okay. Where are my... There we go. All right, so this is clearly not gonna work. I don't think it's the RNG that's slowing us down, right? If I just said if counter equals is greater than or equal to 5, stop, that wouldn't fix anything, right? Right, it's the n squared over a really high number of particles that's costing us too much. So, how do I want to do better? I could measure the density in each region. You know what I mean? Like, I could break the space up into little boxes and measure the density of each box. And then use that as a probability for killing particles, and then decrease the density of the boxes as I go. That doesn't sound so bad. So we will allocate a grid, just clear it to 0, scan all the particles once, increment all the boxes for each part, depending on which particle, wherever the particle is, we increment the box that it's inside of. Then we scan all the particles again and look at the probability of killing it relative to the box that it's in. And if we kill it, we decrement the box so that other particles in the box will be okay. And we can also look at neighboring boxes or something if we want to add a concept of radius. The other way we could do this is I could go for, like, you know, a space indexing kind of approach. Create a bunch of boxes. Each box is like a bucket. Put all the particles into one of the buckets. And then when I do this, instead of scanning across all particles, I'll just scan particles in the surrounding boxes. Seems like a lot more work to create those buckets rather than just the counters. So let's try this. We want a density grid, which will be based on, we're going to need a scratch arena. Do we have a scratch arena in this scope already? We do. Perfect. And let's do maybe like this. I'm just thinking I want the size of the density grid to scale with the screen space being used by the box. So density grid width will be the seal F32 U32 of screen box dim dot x. Let's say I want about 4 pixels in each box. How about that? So now we get a counter for each of these. Now we're going to scan the particles once, not a double scan, a single scan. And for each moving particle, we're going to say, figure out your grid X by doing, first of all, we need to figure out your, right, we're going to do PRT P.X times X form X scale divided by 4. Same thing with the Y scale Y, grid Y. And This only works so long as p.x and p.y are based on 0. So this is still not correct. We don't actually have an abstraction yet between these two rectangle spaces. So we got to come back around to that and do that better. But let's keep working on the density rule for a minute. Grid X, grid Y. So we want to go into our density grid. We want to do grid Y times density grid width plus grid X plus equals 1, right? We just increment each cell in the grid based on where the particles that are currently alive and moving are located. Then we do a second loop over the particles. And here we grab the grid X and grid Y again. And we're going to look at this and say if the density is greater than 1, then with a probability that grows with the density, we'll stop that particle and we'll decrement the density by 1. So how does that go? Is that reasonably fast? Is that doable? Okay, so that works. No n squaredness. I think we need to tune up the density that we're expecting to allow. And I think we also just want, we still want to kill things when they're moving too slow. I think our tolerance there might be too low. We might actually be happier with like that. And let's say that we're even more likely to kill off particles when they get overdense. Okay. We want to add in a rule that says do not allow particle spawns in very low velocity regions as another rule. But 1.2, what if we go with like halfway? Okay. Okay, that's getting better. Let's really get aggressive here. Say like this. There we go. And the other thing we can do is we set that n super high to test this stuff out. Let's put it back to where it was. Okay. I think we could actually allow for a little more slow particles now that we've got that. We could also keep on tuning them to be smaller, more precise. Let's turn the value up on them a little bit. Nice. Nice. Okay. Okay, that's cool. Really cool. Okay, so yeah, let's get rid of all the things that don't do anything. I wonder what our particle count is right now. How many particles are we putting in a particle system? 5,000. So what I want to do is I want to eliminate this. Grid width and height here don't do much, right? So we're just going to play with particle count directly. And we're going to say, like, what if we got away with 1,000? Would that be enough? Is that how many we're actually using? Nice. And, you know, we could do some other things if we want to decrease the density further, because I'm still feeling like it's a little dense. We could have the density granularity parameter live right here. Yep, this version can go away. And then we could up this, and that'll help keep density down more aggressively. Cool. And come on, give me the thing where we got a mouse. Okay, there we go. Up here where I'm calculating D, what if we started speeding things up? Could we handle a faster flow field? Yeah. Nice. All right, so now that we've done all that, I want to look at my to-do list. Screen space density, particle death, good. Do not allow particle spawns in very low velocity region. So what's tricky about that is particle spawning is occurring up here, and so what we're going to need to do is we're going to need to start pulling out our velocity function. So yeah. Right. We do something like this. Okay. So now what I can do is I can rely on the fact that the velocity is known from the position sort of functionally. And when I spawn in a particle, I calculate a position, and I can say test if the velocity for this position is, we have a min velocity. We're also going to have a spawn min velocity that can be a little bit higher, right? Like this or something. And we'll say get the length, if the length from the velocity is greater than the spawn min velocity, then we'll do that. And we'll just try like five times or something like that. So that should prevent it from spawning things in this section. If you're looking here, I think there's kind of a bubble here that we can see that's like we're not getting spawns there, we're only getting deaths. If we wanted to, we could be more sure by saying let's raise this up to the point that it's significant, like e negative 1, and this up even higher than that, e negative 1. So that's just too high, I guess. Won't spawn anything. Alright, so there we go. Now it's not spawning. Here's the radius of the death region, and our spawn region must be something like out here. If I, cancel. If I wanted to, now I could start shrinking this back down. I think we had this at like this. So these are allowed to get way down in here, but they're only spawning way out here on the edge. Right, in the really fast zones. And that's not about the radius. I'm not setting a radius, I'm setting a velocity. So if we change the equation, the spawn velocity thresholds here would correspond to the new velocities of the flow field, not to like the center of the box or anything like that. Okay. But let's shrink this a little bit so it'll spawn a little bit more all over the place for now. Might be a fun parameter to be able to control per visualization when this is meant to be reusable, but I'll let them spawn a little more freely for now. Cool. All right. All right, let's work on this abstraction between the coordinate spaces again, because our abstraction is not very strong yet. I want to get a little more bit more specific about how much detail is available. So we've currently encoded the abstract space that we're dealing with as a single fixed thing for the whole program, which is a fine starting point. But I want to start being able to imagine what it's going to look like when more than one of these exists in the same visualization, and therefore we need to be able to have like dropped these constants down into variables. Question, what computer are you using? I think that's an odd question. I'm using a computer I built. Here, I'll show you. I'm using this one right here. If you have a more specific question or you want to clarify what you're asking, go ahead. It's Windows 10. Desktop. Configuration. What do you mean you're asking about configuration? Like, I've got, I don't know. I'm not much of a computer head. So I've got a graphics card in there. I've got a CPU in there. I've got all the basics, a monitor and keyboard, mouse. Do you want like CPU? Do you want to know which CPU I got? I got it like 4 or 5 years ago. So it's probably not anything cutting edge or fancy. Let's take a look. Here we go. Let's see. Processor. AMD Ryzen. 32 gigs of RAM. 64-bit operating system. Abstract. So that's the abstract rect, and then we're going to do screen rect equals video width minus screen box dim.x times 0.5. Video height dim.y. Plus. Let's do this calculation real quick. So this will be what? Box transform from rect, abs rect, screen rect. All right, to calculate our box transform, what we have to do is we have to say, this is the equation we're ultimately going to apply, right? We're going to say q dot x is going to equal p dot x times, well, let's do this. Q is going to equal p times scale plus off, right? And we want, so this is how the transform is structured. This is how we're gonna, this is the effect that we want to have. We want Q to equal P minus source times the scale plus the dest. Right, so we need to rewrite this in this desired. This is the structure of a transform. This is the structure of what we actually know we want. So the rewrite here is dest minus source times scale, right? So now these two are equivalent, but this one is in the same form as this. So we know what we want. We want x form x off to equal dest.x minus source.x times scale, or x scale, right? X form.x scale is going to just be the x scale. Y off, y scale, y scale, y scale, F32x scale, y scale. So the scales are going to be dest.x1 minus dest.x0 divided by source.x1 minus source.x0. And then x becomes y. Return the x form. This is x0 and y0. Yeah, it's a fine CPU. I think in my experience when coming around to building a computer, I don't end up noticing too much the CPU that I pick, except up to like you notice it when you're measuring the speed of stuff, right? If you have something with 4 gigahertz or whatever. The thing you notice, though, the thing that does come up is the motherboard. When your motherboard arrives and it's busted, or it only half the ports are working, like that stuff is what actually matters to me. Like how much stuff works properly has a lot to do with the motherboard. So yeah, watch out for that. All right, so if I did that right, then it should be calculating the transform from those rectangles. So there it's doing that. That's good. Now the question is, if my absolute rect could be different, right? If I was not using a unit square, but I wanted to use the range 0 to 100, say. Let's actually do that. Just to see some things break. So this is not surprising. Let's go look at vel from pos real quick. Right, so this is still assuming that P is on the range, or X and Y here are on the range from 0 to 1. If they're on the range from 0 to 100, then we would want to do this to make it behave the same, to look the same. Now the velocities are really low because they're like 100 times smaller. So if we did this, we should get the same thing we had before. Except when we go to yeah, this is all fine. Let's try to get off of this. Abs rect x0, abs rect y0. So we are spawning based on Um, abstract, there we go. Density, granularity. Okay. So none of this has changed, except, yeah, the X scale, Y scale stuff is all the same still because we haven't changed the base. Right, so what if we did 100 to 200 was the range we're actually interested in. Right, so now it's no longer safe to assume it's based at 0. Then we'll start to really find stuff breaking. So, vel from pause. We'll leave it the way it is for now. So we should see everything kind of going up and to the right again. But we can't because it looks like this. Interesting. Stuff spawns in and dies right away. So it's probably the density thing. It's my first guess. What if we take that out and see if that lets things flow? There we go. Okay. So yes, the density, this is what it should look like, except that density should be getting applied. But when we apply density, it isn't correct. And that isn't surprising. When we look here, what's happening is we are trying to map, we have a different transform, basically, right? The transform that we start with takes us to the screen rectangle, but we want a density rectangle. And the density rectangle is going to look like this. It's always going to be based at 0, 0, and then it's going to have grid width and grid height. And so then what we want is we want a transform calculated from going abstract rectangle to the density rectangle. And this will be our density transform. And now when we grab this, we can just apply the transform. Like this. And the results include all the scaling and the offsetting automatically. Right, so this becomes our new method of calculating grid X and grid Y. So there we go. That is applying density, and it's applying it correctly. And then vel from position, since our finite domain is now I'm going to make the center just be a little bit off, just for funsies. Right. So now our abstract space is modeling the region from 100, 100 to 200, 200. And it's showing up on the screen like this. Now, there is one other thing I could think about doing, which is, as long as we're doing this, we should probably render it in math orientation rather than in computer orientation. Math orientation says that y goes up instead of down, but computer orientation says that y goes down instead of up. So they don't agree. But I think we can fix that pretty easy. As long as, let's take a look here. Rect F32. Yeah, so Rect F32 is making sure that the min and max are a certain direction here. Why don't we say then that y0 is going to go to y1. And you're going to use the negative y scale. Or we could calculate the y scale with this inverted. Right. So now, if I look at my box range and say I want to range from -1, 1 to -1, 1. And I want my equation to be that ooh, we got a bad. Knighton asks, I imagine to mention your username is misspelled on purpose. That is a fun story. So I made this username when I was like 11, and I've always been a terrible speller. There's no denying that you know I am a typo. I am not skilled with language stuff, and memorizing the spelling of English words is one of the hardest things. So that's just, you know, we can just admit that up front. But I actually, when I first used the username, I spelled it correctly. And like, it was one of those things where I was like 10 or 11, like I said, and like a month later, I forgot my password, didn't know how to do the like change your password flow with my email yet. And I saw that someone else had the username I wanted, or the one that I was sort of confused. Like, I thought I had this one, but maybe this is someone else's account, and they just happened to pick the same username. So I just decided to make another account. And since I wasn't quite sure what the correct spelling was, I just decided to use the other one. And it turns out I had it right the first time. But I've stuck with it ever since, because I think it's appropriate that it's misspelled, since I always have a tendency to misspell things anyways. Okay, so our problem here seems to be that we're getting a negative value for p. Which shouldn't be happening, because it might be because we're flipping the y-axis, though. Let's take a look. It looks like something might be happening that we don't want. Come in here. So our let me think this through. The The transform calculation right here is what's curious to me. So we're now taking a source rect of -1 to 1, 1. So that'll give us a 2 there. This gives us a range of 84, so we get like 42, right, is our x scale. 84 again, but with a -1 on bottom, we should get -42. Okay. Now, source x0 is -1 times, so we get -42 plus the 0 here, so x off becomes positive 42, because this is a -42, that, okay, and the x scale is positive 42. Positive 42, -1. So if I give you a -1, what you're going to do is you're going to multiply it by 42, -42, then you're going to add in x off and you get a 0. Okay, if I give you a -1 for the y value, what you're going to do is you're going to take x scale, which is -42, so y off becomes positive 42, y scale becomes -42. So if I give you a -1, you're going to multiply it by -42, and we get 42. Then you're going to add in 42, and we're going to get 84, which is the maximum that the dest would allow. So when we get hold on, it's like right here somewhere at some point, one of these p-values must be coming out negative. But maybe I'll just wait until one of them hits. Okay. So yeah, we are getting a -1 there for the p.y. So I want to see what was PRTP. That is outside of the legal range, right? That's not fair, because that's outside of the legal range. So why do I have a position? Oh, you know what? It does the kill for this based on the old position, and then it does a delta. Okay. So a couple of things. One, whenever I do that X form, if I'm doing something like this, I suppose I should probably do some aggressive clamping, right? This should get clamped to the range of the density rectangle. Possibly even like this. Because for this purpose, it's not safe. For this to be allowed to go outside of those ranges. So that's thing number one. Just make sure that's happening. And then thing number two is when we are updating moving particles, we're applying this rule here. Let's look at calculate next P. Calculate the delta. Next P is going to be P plus the delta, and we're going to use next P instead of P to decide whether or not to end the particle. All right. So there we go. We just have the differential equation. This corresponds to the differential equation with two parameters that looks like this, right? And we're mapping that on the range -1 to 1 to see what how the field, how particles in that field move. So that's looking pretty good. The and we did this. Okay, so there's our visualizer constructs. So I think we are ready. We are at the point where we can start playing with the differential equation parameters themselves and see what we can get out of that. So let's look at abs. I kind of want to put, I don't know if this will work, but I'm going to try it. I kind of want to put all of these right here because they relate so closely to the equation itself. Okay. And then let's say I want to look at a range like this, 0 to 0 to 1, 0 to 1, and we're just going to look at this is all cool, but can I get predator-prey system? Okay. Density of the prey species at time t, that of the predator. We can interpret rho as the intrinsic growth rate of the prey. It's the death rate of the predator. Okay, so this equation, here we go. Look at me, I'm checking the spelling of predator. I don't know if you knew that's what I was doing just now, but I was just checking the spelling of predator. So growth rate of x minus the predation rate between x and y. This is the natural growth rate of y in isolation. Yeah. Okay, I see what you're doing. I'll do it your way. Right? So now if I define p A, D, and B. Like this. Our delta x and delta y can now be P times P dot x minus A times P dot x times P dot y times P dot y B times P dot x times P dot y. Let's slow it down just a little bit. Speed it up more than that. There we go. Now, the space that we are evaluating this in might not be large enough to capture the interesting shapes that are happening outside here. It looks like there's kind of a point there that might be worth seeing. I picked one for everything. Let's say we want to look at, this out to 5. Well, there we go. Yeah, nice. So this is really cool because we can feel, if you looked at this as a bunch of arrows, you'd see the huge arrows here and the small arrows here and the circular shape. But now we can really feel how the how this thing is shaped with like relative speeds of things, right? We can feel the speed of change here. So if I remember correctly, X is our predator or our prey. So if there's just a lot of X and no predator, our prey species just explodes indefinitely into the future, right? Just like growth rate exponential. If we have prey but no predator, we just get it dies out real fast, right? Then if we get like a mix of them, if we've got a lot of them, we start getting these like spinning shapes. This is really cool. So now what I wish I had was the sliders for changing my parameters, right? But this is what I wanted to see. Let's make the space a little bigger just so I can see more. Decrease the rate a little bit. I think this range is actually pretty good. And there we go. I have no idea if Twitch is even getting close to keeping up with the yeah, when I'm looking at the Twitch version, it's like it's so washed out and kind of grainy. Seeing this like on my own screen is real cool. This is going to be a cool demo to like be able to see in person versus how it looks when you watch it over a video. Yeah. I'm just going to sit and appreciate this. This is cool. I want to be able to get to the point where I can play with the parameters and see the shapes change. Let me see. How much time have we put into this today? Almost at 3 hours. I'm trying to think of what would be a good thing to do, right? So we've got... I could do another 15 to 30 minutes. I should probably wrap up then and get on to other work. This is cool jam stuff to do, but I do have other stuff to do. Well, you have tomorrow, but I think what I'd really like to think about is what can I do in 15 to 30 minutes to get a lot more out of this. Having the ability to control the parameters feels like the first most obvious thing. I could animate the parameters with my code for now, just to at least see like what happens when one of the parameters is changing over time. I could I could just go and track down some other cool differential equations to visualize this way. What's our best option? I feel like having some kind of controls to move the parameters around is the next thing that will pay off the most, because seeing this is cool, but you want to be able to then feel like, okay, can I get some like labels in here? Can I get some knobs to play with so that I can see how these parameters are fitting together to affect the shape that I get. So I think thinking about how I will move towards parameters might be the most important next step to the payoff here. This feels less important now. I'm perfectly fine with the way the particle system is kind of shaking out for now. I think let me start by just like learning a little bit about like what happens if the prey grow twice as fast. I just want to play with the parameters myself and see things change. So that shifts the central point up. Oh, that's so cool. Okay, so what if, let's do this. Let's do differential equation forms. So we want diff eq viz diff eq form Lotka Volterra. That's gonna have P prey growth, prey predation death, predator death, predator predation growth, right? So those are the 4 parameters, and what we'll do is we're gonna start saying like, okay, differential equation forms, diffeq_viz main variables. Make an enum. We'll make a type def v2 f32 diff eq function is going to take a p and params like this. And so then we can have like function v2 f32 diff eq Latka Volterra v2 f32p params, right? And let's drop diffeq function and diffeq params like this. Drop our forms right here. Put these, let's see, where do we want these? Guess I want them right here above the tick functions. It's a little bit annoying because I don't want to have to bury them here. Maybe what I should do is just go diffeq forms.h like this, right? And just start like this and then go diffeq. Yeah, I'll just put these separately because the order of them is kind of confusing and weird. Go like that. The relative order between those and the rest of the program is not something I want to think about. So separate file solves the problem. On we go. I want to grab this as the body of this. Except now we're going to go like this. P params. This is P prey growth, P prey predation death, P predator growth or predator death. Predator predation death. diffeq forms. And then down here, we have this function can go away, diffeq viz vel from position goes away. Move these back up to the top for a moment. I don't like it, but I will get them into a struct eventually soon too. So now that should break. Type def. Hmm. Params. There we go. Growth. This is now going to be if vars diffie qfunc does not equal 0. Run the diffie qfunc here. And pass in the params. So I think we can do the same thing here. Diffie qfunc params gives us a velocity. And then over here, during init, we're going to do vars diffie qfunc is going to be our Latka Volterra function. And for now, we're just going to allocate a Latka Volterra parameter block onto the permanent arena. This will get more sophisticated if we keep building this thing, but this is a good way to get it going for now. Prey growth, predation death, predator death, predation growth, 2, 1, 1, 1, right? Actually, I'm changing my mind already. Let's do it like this. Right, we'll grab one of these, make this the params, like that, stick that there. And we're gonna set that right here every frame. Okay, and the reason I decided to do that rather than allocating it during initialization is because now I can change those parameters from frame to frame with an animation, right? I can do something like this. We have the vars frame count. Now that's going to be an integer. Let's cast it to a floating point. And let's say we want a loop that's going to take 10 seconds. So divided by video FPS times 10 divided by video FPS times 10. Right, so this is going to give me an animation t value that loops from 0 to 1. And then what I can do is have this on like 0 to 1. I can have this on a cycle like that. So now we are interpolating. We are moving from, so let me just say, we want to be able to say like seconds per loop. It's currently 10. Let's just make this extreme right now so that I can see it right away. frame counter, not frame count. That's my mistake. Okay, so that's way too fast now. We can't tell what's going on, but it's definitely doing something. And it's kind of cool. Let's see what happens if we have it gradually changing over the course of 10 seconds. So our prey is going back and forth from having a growth rate of 1 and 2. Right? Our prey grows this way. It grows faster, and the bubble moves up. It grows slower, and the bubble moves down. Curious if we have it go back and forth. Oh, I was having it go back and forth over a larger range than I meant for it to. Let's have it do this. Alright, so that's if we're moving this one around. What happens if we move predation death? I'm going to speed it up just... I don't know if I want to speed it up. Predation deaths. Well, first of all, let's just see what happens when that goes to 2 as a fixed thing. So now... it looks like when there's a lot of predators, these come shooting in much faster, right? The prey dies out really fast when that number is higher. Nice. Nice. That's really cool. So like when it gets really low, it's down to like 0.5. The lines start shooting up because it just takes so much prey in order to, or takes so many predators in order to maintain that population, keep that population from growing in. Right? Like they're going up at those really steep lines sometimes, right? Like right there. But then when it gets higher, it comes down fast. Nice. Okay. What about these ones? Predator deaths. Right now, we have them dying at a rate of 1. What happens if they die at a rate of 2? So that shifts the equation down harder this way. The equilibrium it cycles around is now shifted over here. So more prey survive at the equilibrium point now. And again, if we animate it, it's real cool to watch. Again, I don't know how good this looks over the stream, but it's gonna be real cool, and then you can just play this on your own computer and see what it looks like without video compression. Like, When I pull up the stream and look at it myself, it's just like white. The color is just totally missing. It kind of gets the right shapes, which is cool. Okay. Almost done playing with it. I think playing with it was the right thing to do to end the day. It's satisfying. We got to the point where we could play with it. Proof of concept that the animation of the parameters can work. So maybe tomorrow we can add some like controls to switch between different different system types and change the parameters on them over time and stuff. Or manually change the parameters as sliders, something like that. Some kind of controls for that. So here, when the growth rate is higher, well, now we have things shooting up fast. You see that there? Like, because the predator growth rate is high, they shoot way up. So I want to do like 1.5 plus sine f32t and 1.5 minus sine f32t together. Nice. Oh, this is pretty neat. All right, well, I think that that's where I will say we are done for the day. The next big tasks are to fill out more differential equation systems here and to maybe try to build some controls for like the parameters and switching between which one you want to be viewing. We might also, like right now we're doing two parameters in a unit square, but we might also want to do something like two parameter barycentric coordinates. So you have like a triangle and your two parameters represent sort of two of the three I don't know what you'd call it, sort of coordinates or blend variables that, you know, span over a triangle and have equations that work that way too. You know, there are cool ones like that. So we might want to like play with the different form factors of the space here and maybe try to build controls. Although building controls is a big task to do from scratch. I don't have a built-in UI library to my code base yet, so it's not like I can just start dropping floating point tuning controls and animating things on a timer and stuff super easily. So maybe the thing to do will be to just have like config options. Maybe we could do command line parameters or something, so you can launch this in lots of different ways with different equations or something. We could also try building like a little scripting system, so you could just put in, instead of having to say Latka Volterra, you would just say, here's the, here are the two equations I want, and it would evaluate them using an interpreter. That could be cool, because then you could launch it with like a parameter for the x equation, a parameter for the y equation, and see what you get. Although then you wouldn't be able to animate it like this necessarily, unless I also give you the ability to use a t variable. But yeah, we could do a command line based control system for this to get it to the point where you could actually use it to visualize stuff yourself if you wanted. It's just like a baby starting point. I think it might be cool to slow this down a little bit more, and to also, we don't need these, we could drop the rate by a lot. Let's do 2 there and 25 there. Alrighty, well, it's a good note to end on. We got stuff to do for tomorrow, so I'll make a to-do list. I also want to, just for fun, because this is kind of cool, take a little screen GIF. All right, let's do some to-dos. Controls for changing the diffeq parameters. This is going to include make the abstract space not fixed, command line parameters, maybe a expression interpreter. That might be too much to ask for in one day is the thing. Like, I don't know. It could be that it's just a simple parser. Like, we get some numbers, we get x, y, t, and some functions like sine, cosine, log, etc. It could be, and then obviously your pluses and your timeses and your subtracts and your divides, all those things. But is that really going to be something I can do in one day, or would it be better to just focus on making it really easy to run the couple of built-in ones that we've got? I don't know if making a UI system is really going to be viable in this amount of time either. But it would be cool if you could specify maybe the expression. I don't know. We'll see. But I think something like this will be the plan for tomorrow. And with that, I think we'll be done for the day. So reminder, if you've been hanging out and you're liking what you see and you want more of this, all the code that I'm working on right now will eventually be free. But if you wanted to see it right now, it is available to members, who have become members of the Mr. Forth Lab. It'll be available today right here. You can become a member over at mrforth.com/membership. You can see on this tier here, you get access to the Git repository, full things like the stuff I worked on today. And there are other cool things you can get if you become a supporter or a member. So consider that if you like what I'm doing. This is how I fund all of this. This is how I am able to work on projects like this for the Jam and also other projects. I listed a bunch of them over here on my blog about the membership system, projects that I'm working on. If any of these are things you'd like to see me make progress on, your support helps with that too. Alrighty. Thanks for coming and hanging out and checking out what I'm doing. See you later.